So I guess you've all had 7 minutes now to look at the syllabus. Do you have any specific questions that you wanted to go over or topics for review? So I guess I should preface. Today we'll do review. Wednesday we'll do either more review or something else, I guess, depending on how today goes and what everybody wants to do. But does anybody have any specific topics that they want to cover, or questions on assignment 10 or 11? And then I guess we went over up to there last time. But if you still want to go over any of that stuff, just let me know. And then I guess a reminder that the exam is on December 7th, next Monday. Basically normal class time, 10:10. What's like the main difference between bubble and insertion, and why would we want to use one over the other? Fair question. So bubble sort, basically, my answer is you should never use either of them. Maybe bubble sort, and there's one real case, which I still don't think I'm going to say out loud, just because it's a question on the write up for assignment 10. But I'll at least hint at it. So insertion sort, I would say never really. There's never a good reason, but the main difference between them, at least fundamentally, in like the philosophy between them. So if I do bubble sort and insertion sort, and I do it on the same list. So let's say it's 0, 7, 4, and then 3. And then I do the same thing here. The idea with insertion sort is that it sorts things into their correct place starting at the front, and bubble sort moves things to the end. So if I was to do the first iteration of bubble sort, what it would do is bubble, so this is where the term comes from, it bubbles up the number. So it takes the maximum at each point and then bubbles it up. So at some point, what's going to happen is the 7 is going to bubble past the 4 and then bubble past the 3, and it's going to end up at the end. So the thing about bubble sort is that it basically picks the min of the list and then puts that in the correct place, and everything else just kind of swaps downwards, really. And so it kind of like bubbles it downwards. So you'll notice that like 7, what's kind of happening here is I'm taking 7 out and then I'm moving it to its place, which is at the end. And that's what bubble sort does every single iteration, is it always just takes the max and moves it to the end and then shifts everything else downwards. And it does that by pouring through the whole list. And so if I was to do the next iteration, it would go and it would move. I guess it would be easier if I did it downwards. And it would go and it would move 4 to the end, because that's the next biggest number in this list. So after every run of the outer loop in bubble sort, that many things will be sorted. So we have like the 4 I equals 0 to length, and then, oh, that looks bad. For I equals 0 to length, and then we have like for j equals 0 to length. The I represents how many things have been sorted so far, and then the j just traverses through the list and finds the max. So in bubble sort, the philosophy is that it always takes the max and bubbles it to the end. And then you can see here, like for this example, right, that even though we're guaranteed that 2 of them are sorted, we can actually kind of just see, from an outside view, that it's already sorted. So this seems to be an advantage with bubble sort. Remember, there was an implementation that they hopefully did in 135, and that we did at the beginning of the semester, where you can keep a Boolean that checks for a swap, and then, if there's not a swap, does something. And I'll leave it at that, again, just because there's a question on assignment 10, and I'm going to try not to give you the answer. But that's really the advantage of bubble sort, and the one reason you should use it. Which is basically if you know in advance that you're going to trigger that because your list is in some certain arrangement that would favor that, then bubble sort's probably pretty okay. It has a time that is pretty good if you're lucky. But the thing about bubble sort and insertion sort is that if you don't have that certain arrangement where you're going to trigger that boolean, then bubble sort's really bad. It's you'll learn about this in 302, but it's what we'd call an O of n squared algorithm, which just basically means that the amount of runtime it takes is about quadratic. So the more things I have to sort and sort n things, then it's going to be roughly n squared in terms of its runtime. And insertion sort's the same. So insertion sort is also O of n squared. And these aren't very good compared to some other. So like merge sort and quick sort, which you'll learn about in those classes as well, are both really popular algorithms because they're not ridiculously complicated, and they're O of n log n, and the key there is that log of n is less than n. So this would be faster in its runtime than these ones would be, and you'll again in that class you'll go over how to mathematically prove that, and show maybe if they go over it, show with like a limit in calculus why one is better than the other. So that really bubble sort you only want to use if you know you're going to hit that condition. If not, you shouldn't really use it. And insertion sort on the other hand doesn't really have that condition because it always was. So whereas this one puts it at the end, insertion sort always goes element by element and then moves it to the right place. So it will start and then put 0 into the right place, which it already is. And anything by definition, I guess, on the first loop of insertion sort is in the correct place because there's nothing to the left of it that's smaller. So it'll basically put itself into the list to the left of whatever element you're on and then sort that list. So the list here would be 0 to start with, and then we have the list of 0 and 7, which is also already sorted. And then the next iteration of insertion sort, we would go and we would sort the 4, so we would move that and kind of like bubble it down. Now this one's not too bad because, whoops, I guess I should make that red. This one, I guess, can potentially be better than bubble sort if these numbers over here are generally big. So I guess it's almost really the same example of it does a little bit better if the list is kind of almost there already. I would still say bubble sort's better because it can exit out early, and this one really can't. So the philosophy, I guess, the difference in philosophy here is that this takes the max and puts it at the end, and this sorts at the beginning by taking each individual element and then sorting it into the list to the left of it by basically finding out which two numbers it belongs in between in that smaller list. And again, I think the intuition is it's almost like if I was to hand you a playing card when you're playing poker, you would kind of like put it at the right side of your deck and then shuffle it to the left until it's in the right place, I think is the explanation I've seen. If that answers your question. Does having no bool defeat the purpose of bubble sort? Defeats the reason to use bubble sort, yeah. If you don't, then you shouldn't be using bubble sort, no. The other reason, and this is a justification you'll see sometimes in computer science, which is sometimes fair, or I guess not computer science, but programming, is it's easy to implement, right? I think most people know bubble sort, and the philosophy I don't think is exceptionally complex, so it's just easy to code is another justification. And sometimes you'll see that just in general for like implementations. It's just, it's less efficient, but I mean, it's easy to code. And if you're writing something that sorts 20 elements, then it's not a big deal if you use bubble sort, I guess. Or even the one without the boolean. If you're sorting 20 things, it's not going to take forever. Now, if you try to use bubble sort on something that's like 100,000, so I'm sure a lot of you are realizing it takes forever for that to run, right, for the assignment, then you're kind of just dead. Yeah, you're kind of just kill your program by using something like bubble sort over a more efficient algorithm like merge or quicksort, or any of the other ones. I know there's like radix sort and some other stuff that I'm not too familiar with that are pretty good. Any other questions, I guess? Oh, one more question. There wouldn't generally be a sorted flag for insertion. No, and the reason being is so bubble sort every single loop it has to pour through the whole array, right? That's what the inner loop does. So it goes from zero to, or like index zero to the end, the length, and so it's able to check every single element. So I guess if we say it has like a verification phase, in order to verify that a list is sorted, what you have to do is go through the array, right? There's no other way to check if something is sorted if I just wanted to do that. And so the convenient thing about bubble sort is that part of its sorting thing is going through the array, so we can merge the fact that we're bubbling along with the fact that we can check the array to see if it's sorted. But unfortunately, the way insertion sort works is it never actually fully goes to the end of the array until it's all the way done, because it has like a for loop that goes through the array and then a while loop that goes backwards, or a for loop if you want. And so it never has the opportunity to check all n elements, and so it can't do that verification process early. Now you would program that in first, but it would be separate from the algorithm, and you would potentially be wasting time if it doesn't have a something that's sorted already, which is really a low chance if we're just saying random, right? Because there's what n factorial, many ways to permute a list of n objects. So you'd have like a 1 over n factorial chance, just assuming it's random, which obviously is not always the case, right? You sometimes get things that are ordered in some way when you receive them. But sorry, to answer your question, you wouldn't be able to write one for that, just because it can't go through the array, and that's needed for verification. Any other questions? And I guess I'll pull open the syllabus too again, just to see if there's anything in particular. If not, I'll kind of just quickly go through everything. Alright, so if you have a question, I guess just stop me at any point, but if not, I guess we'll try to run through these bit by bit. So last time I think we stopped on inheritance, and I think I covered everything up to that. So next part was pointers and memory allocation. So remember, a pointer is just a specific type that rather than hold a data type, it holds the address of that data type. So when I write the code int x equals 4, what that does is it goes into main memory, or whatever memory you're using, and it goes to some random location. So let's just say this is 0, 1, 2, 3, and 4, and it will put it somewhere. So if I do int x equals 4, it will maybe just put it there, and we kind of just use the value and we don't have to think too much about it. But when I use a pointer, so we do that with a star, right? and let's just say I call it x pointer, then I can assign to that the address of x, so ampersand being the address part. That's the address, right? Gets the address. So it's the opposite of dereferencing. Whereas you have a variable and the ampersand gets the address, we have the other way around where the star that takes an address and gets the value. So if I was to print the x pointer right now, then whereas x is 4, the x pointer is 2, and hex 2. So it just represents where it actually is in memory, right? And so we say when we have a pointer that it's just kind of like an arrow is how we envision it, that points to wherever that memory location is of the variable that we have. And then we had the ability to increment these. So if I wanted to, I could say x pointer plus plus, and that's totally allowed. And what that does is it goes down and goes to the next one. So here that would be random garbage. So if I see out x pointer itself would be equal to 3 now, but the value at x pointer is we don't know. So we'll say star of x pointer is who knows, and then the star of x pointer up here was 4, right? So whenever I use the star, it gets the value at that specific place. And so the other thing we had to remember with that was that if I do this with a class, so class, let's just say example, int age, and then we have a string name or something like that. And so if I went and said example pointer, so if I make it a pointer to a class, we'll just call it ex, and then we set it equal to a new example. Then what that does is, again, it just goes into some random place in memory, finds where it can go, and then assigns stuff. So when we do classes, right, it will put the things in the order basically that you've given me here. So it will put the age, and then it will put the name, which will just say, Mark or whatever. And so it puts those right next to each other in memory. So if you go to access the pointer now, it will go and use this block of information. So we have this here. So if I was to take ex now, right, and I wanted the name, I could say something like ex name. And so we use the arrow operator, right, when we're using on pointers. And the only difference between that and the dot operator is that the left-hand side is a pointer, and when we use a dot operator, the left-hand side is not a pointer, it's just a class type, which is a thing C++ specifically does. Right, and so I guess as far as the memory management goes, we've kind of touched here already. If we want to allocate new space, we always use the new keyword, right? So this makes some sort of new space. You can either use that to make a new example of a class type, or sorry, new instance of a class type. So here this made a new instance of the example class. And so it goes and allocates the space and then puts all the variables there, and then goes and gets them for you whenever you access it. And you can also use dynamic allocation to allocate an array. So remember, again, if I just have some main memory like this, I can go and create an array this way too. So I could say integer pointer array and create a pointer of arrays, or sorry, a pointer of integers, and it would be an array. So if I say new int 4, then what this does is it goes into memory somewhere. Let's just say here. and then it allocates 1, 2, 3, 4 spaces for you to use. And then we had the ability to kind of violate and go outside of that in C++, sometimes depending on what compiler you're using. But we were allowed to just, use the array like normal, right? So we could say R0 equals 1, and it would go to the 0th position from that pointer and say 1, and R2 equals 4, and then that would go to position 2 and put a 4 there. And then we could say, like R1 equals 7, and it would put it there. So really it just allows us to allocate our own array, which is just a series of things that are right next to each other. And the other thing I wanted to note, because it came up on one of the assignments, was remember that if I was to take the address of R, which it's already a pointer, so if I did that, then this is always the same as the address of the first thing in the list or the array, because the way that an array works as a pointer, right, is it just points to the beginning of it, and then the index here just tells you how far to go into the array. So with an integer, we know that that's 4 bytes. We talked a little bit about. So an integer is 4 bytes. So when you write 0, it will skip by 0 bytes. When you write 1, it will skip by 4 bytes. When you write 2 is the index, it will skip by 8 bytes and then go read the integer there. So really, when you do the index, all it does is, because it knows they're contiguous in memory, it just skips that many groups of bytes ahead and then grabs the thing. And it doesn't go one by one. Just as an aside, it just goes straight to the place that it's located, which is why we try to use this over a linked list, which we talked about later. I guess the point being here, an array, if we allocate it dynamically, that allocates everything contiguously, and the pointer to the array is always the same as the first element, which is why you should not, if you're trying to do like an element passing, you shouldn't just pass the pointer itself, because it'll always overwrite the first element, which I think a lot of you ended up seeing on that gadget assignment. So the other, I guess, last thing about dynamic allocation was that a common thing to do with dynamic allocation is to allocate only the space that you need, and then worry about the rest of it later. So if I, for instance, wanted to write a list class, I might make an array of 4 things. Let's just say 3, because that kind of looks nicer. And then we keep track of a count that represents how many things are in it, and then a size that represents how much space is allocated. And then we can insert things as we go. So if I wanted to insert 1, and then insert 3, and then insert 5 and 7. I think I'm misspelling that. Insert 5 and then insert 7. What we would do is we would put it into the position that the count represents so far. So we would put 1 first, and then we would increment the count. And we would need to check if we're out of space. So we would say, well, the count is less than the size, so we still have space. And then we would insert the 3, increment the count, insert the 5, increment the count. And then once we go to insert that 7, right, we would end up running out of space because the count is equal to the size. So what we said for dynamic allocation is that we would go into a new space in memory, allocate more space, so let's just say 4 here, and then copy everything over, so 1, 3, and 5, and then insert the new thing at the end. So with dynamic allocation, we can keep an array that holds just as many things as we need without allocating too much space. But this came with the disadvantage of the fact that every time we needed to resize the array, we had to copy everything over, which is kind of slow and requires a bit of overhead for us to go and do that. So there's a bit more time consumed than just keeping a single allocation. So our idea, right, was to allocate more than just one block at a time if we want to be efficient about it, because if you keep allocating one block, you're going to need to reallocate constantly. but not to make the amount that we allocate more space for too big, because if we do that, then we might waste some memory, right? So if I was to add, when I went to go add that 7, let's just say I allocated a whole bunch more space, so I had the 1, 3, 5, and 7, and then I just had a bunch of space over here. If 7 is the last thing I'm inserting, now I have all this wasted memory that I didn't do. So you want to keep the number reasonably, about a multiple of how many things you want it to be. So, I just said like 3 or 4 was probably okay for what we were working with, right? And then I guess last thing on this note is after we finished copying, we said we wanted to like deallocate this space. So remember that the way we did that is with the delete keyword. And if we have an array, you put delete and then the braces, and if it's not, you just put the keyword delete. So like on the previous one, if I wanted to remove this example class, then I just say delete EX, right? And that would just go up here and look at this EX space and then deallocate it. And we said if we didn't do that, so if I was to go and allocate some space again, where I just say integer pointer x equals new integer, which is valid in C++, where you can construct that, it will go someplace into memory, right? It will allocate a new integer with whatever the default value is, probably 0. It will keep a pointer to this, and if we do something like, say, x equals new int again, then recall, or actually let's just say null, so that's something different. I don't know. I went to a different page. There we go. Oh, great, now my pen's broke. Everything's going great for technology today. Okay, but if I said like x equals null, right, this would make this pointer no longer point to there, and it would point to null, which is just nothing, right? And now I've lost access to this, right? So losing access to memory. Without deallocating is a memory leak. So now that 0 is just gone. We have no way of getting back to it if we accidentally do something like set a pointer without deallocating the space that it used to point to. Right, and we want to avoid that as much as possible, because C++, in an attempt to be efficient, doesn't try to fix any sort of memory leaks for you, and allows you to do bad things with pointers. Any questions so far on the dynamic allocation? Let's put the next one. I think that's everything that we need to cover with regards to that. So next part was abstract classes and virtual functions. Okay. So remember, an abstract class was one that you can't instantiate. So abstracts can't be instantiated. And so you would use this if you had some sort of generic description that you don't want to be instantiated. So an example of that, sorry, I just noticed the blue. would be, maybe I'm writing some sort of software that requires a person class. And then we have maybe an admin class and a user class. Is I want the person class to be abstract because it's not specific enough. So the idea being that we want maybe a shared class that has some variables. So maybe this has like an integer for age and string for a name that both admin and user can inherit and use. But we don't want it to be able to be instantiated. And so in C++, you can create a class that you want to be abstract, but isn't actually abstract, which is kind of hard to wrap your head around if you haven't done any other languages, where you can do that without having to, make the functions or whatever. But maybe you want to make a class that has only variable members, and then, we move later into actually making specific versions of it. So recall the way that you have to do it in C++ is if I want to make a class abstract, is that it can have any sort of have some sort of members, so string name, and then in order to be abstract in C++, what you have to do is you have to have some sort of abstract function, which was just a function that has no body. So we have void do something, so this person does whatever, and the way we do that in C++ is we set it equal to 0, and this is marked as abstract, which means that we now can't instantiate the person class, and we can't, or because we can't use the do something function because it's not defined yet. So you go and define that later. And the other thing we had to do in C++ to make sure that we mark it as abstract is that it needs to be virtual, and virtual meant that we would be able to change it later. So the other word that they use is pure virtual, though I usually use the word abstract because that's what other languages typically call it. Right, so virtual just meant can change later. So if we need to implement it later and make sure that it actually has a body, it has to be marked as virtual in C++. And so if we have this abstract class, this is now abstract function, this is now an abstract class, and if we want to make any of its children or derived classes to be non-abstract, then we have to actually implement this function later when we go and inherit from those. Right, so let's see, some other stuff we did with those. So let's say class example, and then void use, I guess I need to be virtual. Use equals 0. So remember, when we have only abstract functions, with no members and no other functions, then we called that a pure abstract function, or pure abstract class. Just pencil that in at the bottom. So for instance, EX here would be a pure abstract class because it contains only abstract functions. As soon as I go and add anything else, then it's no longer food. Then it's no longer a pure abstract. but it is still abstract, right? And then last thing, if I want to write a class. If I wanted to change some things, so if I wrote a class A, and then I actually do implement a function, so I call it void foo, and it just counts, let's just say A. And then I inherit from it then recall, so if I rewrite this function, so if I write void foo cout B, and then I go over here and write some code. So if I went into main and then, or you know, wherever, and I wrote something where it was an A called A, and it was equal to a B. So if I create a variable that should be a B, if I go and call a.foo, then that refers to this one. And if I wanted that to not be the case, then what I would have to do is mark this as virtual. And if that was the case, then when I call a.foo, it will refer to that one. So virtual right means that we can override it. So despite the fact that this variable is a B, maybe I should use a different name. Let's use x, just for the sake of the example. XX. Then if this was not virtual, then it always goes with whatever the type of the variable is. So here, the type of the variable is an A, even though the variable itself is a B class. Then it will go and call the A version because it wasn't virtual. But if it is virtual, then it will go and it will use the overridden version that corresponds specifically to what this object actually is, which is a B. So here, this would actually go and call the B one if we did mark it as virtual up here. So generally, I think it's a good idea to mark your functions as virtual if you plan on implementing them again later. Otherwise, you might end up getting some unintended effects where you know, it uses the base class version even though that's not the case. And so the reason we do that stuff on the right here, just to clarify, was this was an example of upcasting. So we go from B, which is a derived class. So upcasting. We go from B, which is a derived class, to A, which is a class that's above it, so to speak, in that class tree. And so this was allowed, and we could do this if we wanted to have, you know, something like the last example where we have a person pointer, and then the person pointer can point to a user or an admin or whatever you want it to point to. And so you can kind of have like a shared class, right? So the idea there with the virtual was that we don't have to have it do the base class version, and we can actually have it have specific code. Any questions on the virtual or abstract part? Next part was operator overloading, and then we did exception and handling last time. So I'll skip that unless anybody has any objections. Operator overloading I don't have a whole lot to say about, probably. So operator overloading was just for readability. So the example we did was we said if we had a fraction class, now that's something that's typically something that most people know about and, you know, understand the mathematical operations like times and divide and plus and all that, right? And those have like a numerator and a denominator. then if we were to write code for this normally, we would have to do fraction f1 and fraction f2, whatever those two things are. And if we go with what we're used to, we would have to write a function called add f1 and f2 in order to write whatever it is that adds these two things together. And that's fine. But the idea was that if we do an operator overload, then it allows us to write something like f1 plus f2, where we can use the normal operators that are defined in C++ and then use those instead of writing a function that does it. Basically, we just write a function that has a special syntax. So the way we did that was we would say something like, basically like the same as a function, so we would give the return type. So here it would return a fraction. I guess maybe I should go and do this off to the side somewhere. So we want it to return a fraction type, and then we give it the name, which is operator plus, and then we give it the argument list, which would be fraction other, something like that. And then we would be able to actually go and write whatever code does the addition for these, and then return a new fraction that does it. Right, so basically it's just a function that has a special syntax. So it would do probably the same stuff that add f1, or sorry, add f1 f2 does, but it would just be written that way. And so the only other thing to note about that was just the fact that if I write, we'll just use the fraction class again. I'll say n and d. Was that if I write it as a member, so if I say public, I guess, public, and then I write the operator plus, then recall that the first argument is implied to be the object that's calling it. So the first object is the caller. So member, and so when we call it, that's called as this plus other. So if I was in main and write f1 plus f2, f2 would be the caller, so it ends up being this, and f2 is this other here. Oh, whoops, I pointed to the wrong thing. Right, so if we make it a member, then the first argument is always implied to be the caller of the function, and so it ends up being this in the context of the thing. But if we make it a static operator, or an operator that's marked as friend instead, which is static by definition, then let's just say minus, then we have no this to call it with, because static implies that there is no this, so we end up using the two normally. And so, you know, if I wrote subtraction, then f1 minus f2, this one would be that fraction, and this one would be that fraction. So the key difference here is if you write it as a member function, the first one gets replaced with whatever the calling object was. And so the last two things I guess to note about that was the fact that there were certain functions that had to be written as friends and had to be written as as members. So the ones that had to be friends were, at least I think these are the only ones, were the extraction and the insertion. And the reason being is that if the first argument gets replaced by an instance of this object, then we can't use these like we normally would, because the way I typically write this would be like C out. and then F1. And this would be invalid if it was a member because the first argument is not a fraction class, it's a stream. And so if I wanted to make it a member, I would end up having to write it like this instead, where I write F1C out, and that's just, that looks kind of gross, and is also kind of backwards from the way all of the other ones are written for like integers and strings and all that. So you might get a very strange looking syntax, and it might not actually condense properly if you try to do that, and you might make it more difficult to write expressions. So that's not allowed. Those ones have to be friends for sure. And then remember that there are the ones that are required. This one, I don't think there's a huge justification. It's just C++ likes it. Members for sure were the accessor ones. So this one, so the accessor that lets you use it with a similar syntax to an array. This one, which was like a copy, and then the last one was, I think, equal also requires it, and then I guess by extension probably plus equal and minus equal and all those as well. Maybe not. We'll just say equal for now. And so these ones, I guess, just by C++ convention are supposed to be members. I assume that's just because they specifically access data, and it would be kind of convenient to not make a copy with those if you make it a member, or it can be more efficient. I assume that's the reason they do it, but that one I don't think there's as much of a justification for. Right, so I guess key takeaways on this one were really we just use operator overloads because they're nice to read, and they look more correct when you're writing math classes like fraction or matrix or whatever, or if you want to print something, then sometimes this looks nicer, I would say, at least in C++, and that was basically the reason we did it. Or if you wanted to define some sort of operation, maybe if you wanted to be able to add two people and you have something in mind for what that means, then you could write an operator for that. And then the other thing to take away, right, was that members get one less parameter in their parameter list, or member operators. And then we did exception handling last time, so we'll just skip past that. So we got templates, polymorphism, which that's not a big deal. Templates and recursion. Okay, we'll do templates first, and then we'll do recursion. And then the polymorphism part was, I guess, just to throw that out there, was just like a catch-all term, right? So polymorphism is the ability for data to change. And that was a catch-all because that could refer to a lot of things. Actually, we should probably bring this up. So there were two types of polymorphism that we were super concerned about, which was compile time polymorphism. As in the compiler does the polymorphism, and there was runtime polymorphism. So most of the stuff that we've written was runtime polymorphism. So something like what we did earlier, where we say ax is equal to b, so we make a variable called a, but it's actually an instance of b. Then that would be runtime polymorphism, because it would go and basically make this class into another instance of a class, and keep some info on what class it currently is. And examples of compile time polymorphism would be templates would be the big one, and I'm sure there are other, maybe inheritance would be like inheritance of a class. I guess the declaration of it would be compile time, but I would say the big one is templates, which is what we're going to talk about here. So runtime polymorphism is changes in data that happen while the program is running, and compile time polymorphism is polymorphism that occurs because the compiler specifically does it. And so what we'll see here, if you remember, is that templates are an example of compile time polymorphism because the compiler actually decides what it is that you wanted. So remember that we can write a template class or a template function. And so the way we do that is we just use the word template, and that specifies that the thing we want is a template. And so we give template, and then we give a list of generic types that the compiler will fill in later. So if I write template class T, and then I write the actual class declaration, so let's say class list, and then I just keep a T pointer called data or whatever. Or maybe let's just make this a struct for the sake of making it nicer. So struct. Then if we go and we write list, so the way we use any sort of template class is with these angle brackets, right? So if I wrote T or list int, and I call that variable list, then remember what this does is the compiler, anytime it sees that you go to use that generic type, it says, okay, you want a list that takes integers, I'll go make that for you. So it will go and it will generate new code, basically. Maybe we should show that here. So it will go and it will generate a new struct called list int. And anywhere it sees the generic type T, it will just go and replace that with an integer. So now this becomes int pointer data. So it just makes a copy of the code, right? It doesn't do it at runtime. It specifically says, okay, well, you wanted the code for an integer, I'll go make the code for an integer. And it literally just, it takes the type and it replaces it with the other type. And that's all it does, remember. So if I was to go and write list and then bool, then it will just go and do the same thing and generate more code where the T is replaced with a bool pointer data, and then all the other code that came before and after that. So whenever you write a template, it just literally goes and it replaces it directly, and it does that all at compile time, and then at runtime the type is already decided, so it's able to go and use it because that type exists. But if you don't write a specific type, it won't generate the code for it. So if I didn't write list float here, right? So it's not going to generate a list class for float, and I guess I should call this list too. It won't generate anything extra. It only generates what it knows you're going to need. And so you just have the necessary code, essentially. Now the other thing to mention about that, I guess, pausing, shared, I think I hit a button on accident, was that we can also make template functions. So I could make a template class, we'll just say u. So remember, you can name this anything. It's basically like a second list of parameters that you give it access to. And so I could write a function called maybe void sort that takes in a vector of type u called list, and then it sorts vector that contains u's. And then again, just recall that the way we call this would be sort, and then whatever type you want to sort. So if it was like integer, we'll just say integer, and then I would call it with some sort of vector of int. And again, just recall, all this will do is it will go up to this function, and it will generate a new version of that function that has a integer replacing all of the u's that I happen to write in whatever body of code that I write in this thing. So it'll at least replace this one, and then whatever I do later it will replace as well. Last thing to note maybe is the inheritance with this. So if I write a template class, I can either inherit and make a new template class. So we'll just call it class example. And then I can make a T that's whatever. And then if I go and inherit from this, then I have the option to either make a new template class, or, so we'll just call this A, or I can specifically have it inherit from a specific version. So I could say that it inherits from the integer version of EX, and it will go and specifically first replace all the T's with integers and then inherit from that version. But we also have the ability to define another template here, class T, class U, and we can specify as many as we want. So maybe if I wanted it to only inherit from the T version, which it will again go and fill in later whenever it decides what type you want, then I can go and write whatever other code I need. So we can either allow it to inherit from all versions of the template by also keeping the inherited version to be a template as well, or we can specifically inherit one version of it. So like for assignment 11, which I'm sure most of you haven't gotten a chance to start yet, but that one inherits specifically from a template class, and it uses the pixel class to instantiate it. So the inherited version is only allowed to use pixel type. And so we've decided, okay, that's a stopping point. It's not a template anymore. Let's see, recursion, and then linked lists, and then maybe stacks and queues. Okay, so recall recursion was when we use previous solutions or smaller cases to solve a problem. So a common example of that was factorial. So we said something like 4 factorial was equal to 4 times 3 times 2 times 1, which is 4 times the rest of this, which is 3 factorial. And then we know that 3 factorial is defined as 3 times 2 times 1, which is 3 times 2 factorial. And then 2 factorial is defined as 2 times 1, which is 2 times 1 factorial. And then 1 factorial was 1, which is 1 times 0 factorial, or just 1 if you want to define it that way, and 0 factorial was 1. And there was nothing below this, right? So the idea is if we have a stopping point, then that was called a base case. It's the final thing that we have to worry about, and we can have multiple of them, right? And it was kind of like a stopping point, and it was a defined case that we for sure know the answer to. It has defined behavior where it doesn't rely on any of the previous ones. So whereas these all rely on the factorial before them, this one is defined just by a definition, so we're able to use it as a base case. So recall if I was to write this as a C++ function, then I would do int factorial, int factorial, and it takes a integer n. And what we said is generally you check for the base case first, but that's not always. I guess that is generally true, but you can kind of like mix them in, I guess, if you really wanted to. So we have some sort of defined behavior. So when we take n factorial, by definition, that's 1. And so that was our base case, right? It's where it stops doing the recursion. And then we said that there was the general case or the recursive call where you take return. So remember, just because I got this question a lot, remember that if it's a value returning function that you still need to return your recursive call, otherwise you're not going to get the value that you're trying to get. So here I'll return factorial, or n times factorial, and then by definition this was n minus 1, right? So like 4 factorial is 4 times 3 factorial, and 3 is 4 minus 1, and then same thing with here, 3 factorial is 3 times 2 factorial, which was 3 minus 1. And so whenever we do something that reduces a parameter or reduces the size of the problem that we're working with in some way, then that was called a reduction operation. And it doesn't have to strictly make it smaller. Remember, it could make it bigger if for whatever reason your base case is bigger, but that's kind of strange and not very very common to implement. I get usually more inefficient, I would say. But generally, we have some sort of reduction where it makes it approach the base case. Base case. And so the thing to recall about that is it's not always subtraction, because I feel like I get this question, or I got it kind of often on the last exam. It's not always subtraction. Remember, it's not always subtraction by 1 also. It doesn't have to decrement, it doesn't have to increment. It can be anything that makes it approach the base case. So that could be division, or that could be something more abstract, like just changing the size of something, or modifying your problem in some sort of way. So remember with assignment 9, what we had like a stack of dolls, right? And those work recursively because there's always another doll on the inside until we get to the base case where there's a doll with a null on the inside. So remember, if I have the outermost doll here, then what I could do is I could, if I wanted to open this, let's just say, I would open the one on the outside, and then I would open the one on the inside, and then I would open the one on the inside. So what we would do there, right, is we would, if we wanted to open void, then we would say if the inner, we'll just say inner for the sake of making it simple. So if it's not null, then what we wanted to do was we wanted to open the next one. So inner was an object here, right? So inner open. And so this one looks a lot more abstract than the last one, but we have to consider that this does still have a base case and a reduction operation. So this is the base case in a way. In reality, I guess we could say that the implied else here is the base case. So I don't have an else, but there is always kind of one there conceptually, even if you don't write it. So if this condition is not true, then the opposite is true, and that's actually our base case, right? The base case is when we've reached the inside and it's null. So a little more abstract here. I didn't explicitly write a base case, but it is there, just by virtue of being the opposite of the thing that actually does the recursive call. And then the reduction operation was this one. So there's no subtraction here, no division, no sort of normal mathematical operation. But this is still a reduction operation, because what this does, right, is it opens the doll on the inside. So here, right, if I was to open the outermost doll and I go and open this one, then what I'm doing is I'm opening a collection of dolls that is of size 2, whereas I started one of size 3. Therefore, I'm reducing the size of the stack of dolls that I have, which is a reduction operation. We approach the case which is the base case of specifically one doll where the inside is null. So a reduction operation, right, doesn't have to be strictly like a mathematical operation. It can be kind of abstract It just the definition or the goal of it is that it needs to make it approach the end or the stopping points of your recursive cases. Any questions on that one? I guess I didn't mention the most important part, which is recursion, right? Just means that it calls itself. At least in programming, if you just want to take that away, a recursive function always has to call itself. So open here calls open. And then we have 2 minutes left. I don't think I can talk about too much. Any last questions? I guess the only things we have left are linked list and stacks and queues, which we just went over. I guess the last thing then, if you have questions, we'll stick around. But so I assume this isn't going to take the whole time. Do you want to do something else on Wednesday afterwards, or just more review and like more questions afterwards? Any specific wants on that? And if we do an extra topic, I guess at this point, I think the most common one I got was the development. So I guess first question would be, do you want to do more review after we finish going through the syllabus? And then the second question would be, if you want to do development, what kind of development do you want to do? Like mobile applications, desktop applications, games. I mean, I guess we'd probably have like 45 minutes to talk about it. So we'll try to do something, I guess. I guess that'll be kind of difficult, but any thoughts on that? Well, okay, fair enough. I guess if you have any input on that, there is still that thread open on Canvas, so I guess just leave a comment if you want to do anything in particular after we finish that. I guess on that note, then, if anybody has questions, I'll stick around for another few minutes. If not, I'll see you all on Wednesday, and then we'll just finish doing the last few things for the review.